Cool. Awesome. Phew, tech, eh? So to kick things off, my name's Chris Nesbitt-Smith. I'm based in London and currently an instructor for Learn K8 and a consultant to various bits of UK government and a tinkerer of open source stuff. I've been using and abusing Kubernetes in production since it was 0.4. So believe me when I say it's been a journey. I've certainly got the scars and the war wounds to show for it. So you believe the hype that Kubernetes lets you scale infinitely, auto-heal your cluster, and so on. So your cluster is self-monitoring, it's scaling up instances of your cloud-native stateless applications on demand when you need more. But all of a sudden, your nodes are full. You can scale no more. Well, enter the cluster autoscaler, and of course, a splash of YAML in order to save the day. And that can integrate with your cloud vendor to provision more necessary nodes. And the good news is that the autoscaler is configurable. Though, sadly, as we'll see, it's not quite as configurable as you might hope or expect. There are alternatives, but the official cluster autoscaler only scales up when there's pending pods in order to satisfy the demand, which is probably a good idea since there's little point adding more nodes unless you have the workload that needs them. Okay, so first let's refresh ourselves on how the Kubernetes kind of scheduler works. So if I create a deployment with 2 replicas, I do this by submitting some YAML to the API server, which then writes it to etcd. The controller is watching for this type of event, recognizes it needs to go and create some pods, which it does, and then these are now pending. The scheduler is a component that is looking for pending pods, sees these, and then schedules or assigns them to a node. The scheduling, however, is broken down into a few steps, from the initial queue through filtering viable nodes to then scoring them before actually finally creating the binding. But how does the scheduler know how much memory and CPU a pod uses? Well, it doesn't, strictly speaking. So you need to spoon feed this with requests and limits. So if you don't specify requests and limits, Kubernetes will play completely blind. Your cluster will inevitably become overloaded, nodes will become oversubscribed, and you'll be constantly fighting fires. So if your only takeaway from any of this is that all your containers should definitely have requests and limits defined, then we've at least achieved something useful here. So requests are the initial ask, and limits are the point where the container will be throttled, its CPU, or killed if it exceeds the memory. Okay, so applications come in all sorts of shapes and sizes. So you may have some applications that are more CPU intensive and don't require much memory, while on the other hand, you may have others that have a greater memory than a CPU footprint. So those applications have to be deployed inside Kubernetes, inside computing units, which have, again, their own CPU and memory kind of characteristics. So for every application deployed in a cluster, Kubernetes makes a note of the memory and CPU requirements. It then decides where to place the application in the cluster. In this case, it's on the far left node. If another application of the same size is deployed, well, Kubernetes goes through that same process and finds the best node to run the app. In this case, it picks the right-hand node. As more applications are submitted to the cluster, Kubernetes keeps making notes of the CPU and memory requirements and allocating these applications in the cluster. If you play this game long enough, you might notice that Kubernetes appears at least to be a reasonably skilled Tetris player. So your servers are the board, your apps are the blocks. And Kubernetes is trying to fit as many blocks as efficiently as possible. But what about the size of the worker nodes? Well, what kind of instance types can you use to build your cluster? Well, nowadays, the cloud vendors make almost every instance type available to be part of the cluster. So you've got pretty much free choice. There is a catch, though. So you'd be forgiven for thinking that if you get an 8 gig RAM and 2 CPU node from your cloud vendor, you could deploy 4 pods that are 1.5 gig RAM and need a quarter of a CPU. However, it's not quite so. One of those pods would remain pending, which, if configured, will of course cause the cluster autoscaler to go and create a new node, and then eventually your workload becomes scheduled. But why is this? So when you provision a managed instance, you might think that the memory and CPU available can be used for running pods. And you are right. However, some memory and CPU should be reserved for the operating system. And you should also reserve memory and CPU for the kubelet. But surely the rest is available to my pods, right? Well, not quite yet. So you also need to reserve some memory for the eviction threshold. So if the kubelet notices that the memory usage is going over that point, it will start evicting pods. Your cloud vendor will usually choose these numbers for you. For example, say AWS typically reserves 255 meg memory for the kubelets, 11 meg for each pod that you can deploy on that instance. So this is the reserved memory for the kubelet. So the CPU reserved is usually around 0.3 to 0.4 of a CPU. For the operating system, they reserve 100 meg of memory and 0.1 CPU for the eviction threshold, and another 100 meg. So in AWS, if you select an M5 large, here's a visual recap of how the resources are subdivided. With this particular instance, you can deploy 27 pods. The other thing to consider is all the time that this takes. So let's assume that you've configured your horizontal pod autoscaler, or HPA, in order to scale up your pods dynamically. So, well, that's where the journey probably starts. So to start with, about 90 seconds is what's needed for your horizontal pod autoscaler to react and decide to scale up your application. Then the cluster autoscaler then takes around, say, 30 seconds to request a new node from the cloud vendor. Then around 3 to 4 minutes for the machine to boot. And then around another 30 seconds for it to join the cluster and then be ready to run workloads. Then you can, of course, add on time for pulling your container image that won't be cached on this brand new machine as well. So to help visualize the impact of this, this can have, I made a library last year that actually fakes a Kubernetes scheduler. It allows you to specify many different types of pods and model their scaling dynamics, tracking container startup times, and so on, and define your node properties. So it takes a lot of shortcuts in order to provide hundreds of thousands of intervals representing kind of days, and do that in tens of milliseconds. It's not the real Kubernetes scheduler. Pull requests are very welcome if you'd like to improve it. So to give you a way to play with that, I also made a game as a novelty for KubeCon last year called Black Friday. The scenario is that you're an SRE team supporting a retailer facing a spike in traffic on Black Friday, and then again on Cyber Monday, with a lull between and a calm before and after. So let's actually see some things. So yes, it's a three-tier service of a front-end, back-end, and database, all of which have different kind of scaling properties, startup times, etc. So we can see some of the details here in the hints. So we can see the properties on our node, or different node types, and we can see like the profile of the front end, and similar for the back end. It's a bit zoomed in at the minute on this presentation. So you can see here's my Friday spike, and here's my Cyber Monday spike, and how the heuristics of how that trails off. So it's the goal is to configure your cluster to as closely follow the spike with just enough infrastructure. So failing some requests and getting a few SLA penalties might actually result in a greater profit ultimately. So let's have a kind of play on this. So if I, for example, change my, say, minimum node count down to 1, and similarly, just let's see what this looks like if I drop everything down to start at 1 instance of everything. You can see I can change the point on when I scale up these pods. So let's see. Hopefully that should schedule out, and we'll see some failed requests.
Yeah, love you.
Maybe live demos, hey. Yep, that's live demo failing. Maybe let's go with 2. Right, so maybe. So it's failing to schedule my first interval. I should have. Yeah, cool. Okay, so we can see that in this we've reached a point where the where we've got some failed requests right here, and some more failed requests on Cyber Monday. So this is where my infrastructure scaling and my pod auto scaling failed to follow the spike up of demand as closely as it needed to. So, but that has actually only caused me a penalty in this scenario of $1,154. So in effect, my company's in profit of, based on where it presumed it would be if it didn't have any auto scaling, of about $15,000. So maybe not a bad idea, perhaps. And you can tune and tweak these numbers. So please do feel free to play with this. The odds, may the odds ever be in your favor, ultimately. This is an experiment to kind of play with and try and get your name on the leaderboard. Cool. Okay. First live demo out of the way. So what do we do in order to stack some of the odds in our favor? Well, we can not scale at all. That is always an option and often overlooked. So, or what if we could get a head start on the scaling? So maybe not scaling at all sounds a bit flippant, but what do I really mean by that? Well, going back to our scenario of fitting our pods on a machine, taking into account the reserves for the kubelet, if we sized our machine correctly, we might be able to fit all of our workload in a node. So this isn't easy given the vast array of possible machine sizes. So we've done some of the hard work for you in this space and created an instance calculator. Next live demo. So with this, I can tune and tweak the configuration of my pods. So I can say that I want to look at the efficiency, and how many pods I can fit on it. So I can size my pods up in memory and see that dynamically move around. So I can see that I've not got a particularly efficient node size. Now I can flip around. I can see that other nodes offer a varying level of efficiency if my pod looks like it requires these sorts of kind of properties. And I can densely stack my things. So I can hunt around for different cloud vendors and pick the right tool, pick the right node for the type. And I can optimize for either CPU or indeed for memory as well, and just kind of change some of the properties around them, daemon sets and agents and things like that. Cool. Okay, so finally, on to the topic of this webinar. All the wait's over. It says as his clicker stops working. So what if we could always have at least one node that's ready for when you need it? So removing that 3 and a bit minute wait. Well, to do this, we can create a placeholder pod that as soon as your workload comes along, needing the resource, the placeholder pod becomes evicted, causing your cluster autoscaler to boot a new machine in order to host the new replacement placeholder. And this will continue as you scale into further nodes, keeping you always one step ahead. Okay, now to praise the demo gods again, where I do a real live demo and hope that everything works with a real Kubernetes cluster. I have backup plans of videos if not. So let's have a look. So behind the scenes here, there is a real Kubernetes cluster, and I can prove that in a minute. So we've got a simple application where we can see the effects of clicking on the scale buttons. So if I say to scale to 5, we start with 1 replica. Okay, and clicking the 5, hopefully that should start. Good luck. That's where I cross my fingers and hope that the thing that I built works. Cool, hopefully, so they're pending. Oh, it never works. We have a backup plan. It's fine. Okay, fine. They are all there for the browser, not loading the timer right. So what you would see is this timer starting to count up. We'll ignore it for the minute, but it will add a. We'll check back in a sec. But what you'll see is this timer should elapse to 3 minutes. So if you look at the time of how long we've been talking here, it will be about 3 minutes in order to scale up to have 2 nodes. So in a minute, the cluster autoscaler is going off and asking for a new node. We can do that in a separate instance over here. So I've got 2 clusters. Hopefully, be able to actually at least show you the timer that actually works. It did. It doesn't. Okay, fine. Live demos. Okay, similarly, so assume that this is like plus 10 seconds, the other one's plus how many minutes. Fine, we'll come back to them. So we started one replica, we scaled to 5. So the current node gets saturated with the 4 pods, and 1 is left pending behind the scenes. So now the cluster autoscaler is going to request a new node from Linode. So while I stall for about 3 minutes of what would otherwise be kind of radio silence of me praying for it to kind of work properly, are there any questions I can come to? So Sam, if we create a pre-scaled node for each node pool, would that then cost high, right? So how to turn them off when we're not in use? So yeah, if you've got a node that's hanging around that's basically just running a placeholder, then yeah, you are kind of, your plan is to kind of ultimately waste some money. Ultimately, so your plan is to keep that spare. So this isn't like fundamentally an uncommon pattern that you might be used to seeing in other worlds, where like you might have like a RAID array where you might have a hot spare in that, because sure, you can go and get a new drive or something, or a new blade unit to throw in the chassis. But if you've got one already racked up, it saves you a trip to the data center. So likewise, albeit that's a timeline that normally is measured in at best hours, probably days, we're trying to now shave minutes off. So we're at a better place than we might have been with more traditional infrastructure and hardware. But I'll come to some of that point at the end, how you might be able to lessen the financial impact of this sort of pattern. So mentioned oversubscribing the nodes with requests and limits. How does that work? How does that work when we oversubscribe our VMs in VMware? So if you oversubscribe your nodes in the hypervisor, then you are in for a bad day. I guess it's a very short answer. Kubernetes is not. That's not how it's designed to work. In the same way as you'll notice that Kubernetes does not play well with a swap for memory. It relies on kind of real resource, and you need to really kind of give Kubernetes as much as it can get in terms of empowerment to kind of know what's going on. Which I think, on the first node I can see, so I've got 2 clusters here. There's 2 tabs. So this first cluster's now got its second node, so we should see a second pod. So once that's pending at the minute, I want the other nodes. There we go. Fine. Okay, so that took about 3 minutes. So sorry, I'll just finish off that question. So yeah, you really need to give Kubernetes as much information as you can in order for it to make the best decision. So like help it help you ultimately. Tell it what's going on. That's okay. So as you can see, that took about 3 minutes for my pod to scale from 1 to 5. The first bit of it was done within about 10 seconds, and then the last kind of pending pod took a bit longer. So let's see what the difference is if I use my placeholder pattern. So what I'm going to do is I'm going to scale back down to 1. Should hopefully go and kill all my pods. Cool. And then I'm going to deploy my placeholder. So I'll show you in a minute. This is a real Kubernetes cluster. I've just got some JavaScript and a web page that's like submitting some YAML, just so you've got a visual view of what's going on. On my other screen, I am kind of panically watching the actual kind of the logs and the events. So now I've got a node here. So I'm back down to my original scenario where I have my one instance of the application running, and I have my placeholder pod keeping the other node present. So it's a kind of hack on the autoscaler just to keep like a node available. So now if I click scale to 5, I'll quite quickly see that it's saturated the first node, and in a few seconds, 7 seconds, there we go, my container has now booted, in the second node. So we've gone from kind of near on 4 minutes down to kind of about 7 seconds. Pretty good, right? Oh, cool. Okay, so and if we can turn the placeholder back on, and what that will do in the background is that will go off and start another node. Sorry, the placeholder was already on. Sorry, I didn't need to do it. So the placeholder's there. So in the background, what's already happening is that the scheduler has started booting another node. So we can do that again in my second cluster, which is still showing the number of pods. Fine. Okay, maybe we won't do it in the second cluster because something weird's going on there. Fine. At least I had 2 plans, hey? Cool. Okay. That was the stressful bit out of the way. So, and then the slides don't change. Cool. So to prove that this is a real cluster, this is what was just going on just a second ago, looking at the events that were kind of streaming out the cluster, demonstrating the nodes coming up and down and the pods being scaled up and down as I went. We can skip past these because this is the backup videos that I had of it working. Cool. So how did I make this all happen, though? So firstly, we need a placeholder, and that needs to be big enough to know that it will never be schedulable alongside any real workload on a node. So it should be sized kind of big enough in order to fill the whole compute node. Then you need to specify a low priority class in order to make sure that it's evicted as soon as there's a real workload that comes along and needs that capacity. So the placeholder pod competes for resources. So we need to define that we want it to have that low priority. With a priority of -1, all other pods, kind of even by default ones, will have precedence, and the placeholder is then evicted as soon as the cluster runs out of space. If I flip back, we should hopefully almost maybe be. There we go, bingo. So we've now got our over-provisioned node. And if I scale back down to 1 and turn the placeholder off, we can come back to that at the end and hopefully see that we've actually, the autoscaler has reduced us back down to 0. That will take a minute or so for the cluster autoscaler to recognize that. Okay, so now for a demo of how this works with autoscaling, however, though. So just now we demoed it with kind of point and click to change the replica count. How does this work in a more real-world-ish type scenario where you may have your kind of horizontal pod autoscaling? I'll be honest with you, I have definitely exhausted my credit with the demo gods. So I'm going to be playing some videos here and provide a bit of narration and also save us all hanging around for kind of the 3 minutes or so that it takes. So before I start, to provide a little orientation, on the left-hand side, we can see the requests per second that we're serving. The bottom left, you can see the nodes and the pods on them, and you can see my nodes in here, again, can take up to 4 workload pods. I've got a simple application that can handle a fixed number of requests, and I'm ramping up traffic. As you can see, we start with 2 nodes, and we're able to kind of sustainably handle the traffic as it increases in until we fill both nodes. And it's at that point that the HPA has decided to scale up, and then we finally see the cluster autoscaler in a minute or two's time that I can fast forward, start to actually provide the more nodes that will be required. Skip forward a bit, there we go. So yeah, the cluster autoscaler has now come in and provided the extra nodes. So I've manipulated these results a little so as not to leave you waiting too long, which would be that around 4 minutes for the nodes to be available. So in that time, while we were waiting for the nodes to be available, well, the traffic that we were able to kind of service and, as an application really kind of flattens out. But as soon as we've kind of got the resources, it kind of goes up again, and we can see the recovery curve coming in. Okay, so next round. So in this, so is that playing? Yeah, cool. So now we can compare that to our more proactive pattern where we have a placeholder pod that's keeping us a spare node ready at all times. As the traffic builds up, we can see that that placeholder quickly becomes evicted and our workload pods become scheduled on that node. A new placeholder pod is created as pending, causing the cluster autoscaler to go off and create a new node. So sometimes, however, as happens here, we'll see the traffic build up and the HPA has outpaced the speed at which we were able to stand up the new node. So there you go. So yeah, the placeholder pod didn't actually get landed on the node until sometime later. As you can see, we're adding nodes, and immediately we're not even getting the chance to schedule the over-provisioning pod in them. Though the over-provisioning pod has always made sure that we've always had a request in flight to get a new node. But the result of this ultimately is, as you can see here, is that the traffic steadily kind of paces up. There's some bumps, but we can see that there's no kind of flattening out. So there's no a point where we actually are failing requests at any point. So this all comes at an inevitable cost. Your plan is, in this case, to always have extra capacity ready and waiting for your workload to require it. What might therefore be some better answers, though? Well, you can tune your workload in order to make sure that you're not leaving gaps. Or better yet, remember that pod priority thing that we used? Well, if you've got workload that suits it on your cluster that you'd like to run and would give you more return on investment than just a placeholder, so stuff that can handle stopping and starting when it's appropriate to. So perhaps some housekeeping, some analytics, some machine learning, or maybe just less important services. So you might want to, say, prioritize the shopping cart supporting applications and pods over, say, the customer service desk. Ones that you can structure, actually allowing you to structure your cluster workload to be more aligned to your business benefits and goals. I've been Chris Nesbitt-Smith. Thank you again for joining me today. Like, subscribe, whatever the kids do on LinkedIn, GitHub, whatever. You can be rest assured there'll be little to no spam since I'm much content at all, since I'm awful at self-promotion, especially on social media. CNS.me just points at my LinkedIn. Talks.cns.me contains this and some other talks, and they're all open.